and in this lecture we're going to look at the operation of convolution. So in fact we won't be covering in week 3 all of the topics that are listed in the course outline, but over the course of weeks 3 and 4 we should be able to get through all of the topics listed for those 2 weeks. So let's talk about convolution. Why are we interested in convolution? Well, we know that because of linearity, the transform of the sum of two time domain functions is simply the sum of their Laplace transforms. So the S-domain equivalent, if you like, of addition in the time domain is simply addition itself. It's going to turn out, well, that doesn't hold true for multiplication, and in fact the time domain equivalent of S-domain multiplication is this operation that we call convolution. We've been saying all along that the reason we use the Laplace transform is because it lets us transform problems into problems of algebra. And you know, algebra is based on mainly addition and multiplication. We know that the time domain equivalent of addition in the Laplace domain is addition itself. And the fact that the time domain equivalent of multiplication in the Laplace domain is convolution means that convolution is quite an important property. You've already seen examples of this. For instance, in assignment 1, there's an example of convolution in a discrete time setting. But let's take another example of a discrete kind of convolution. Consider multiplying two polynomials. Obviously, the result is going to be another polynomial. The question is, what are its coefficients? So let's say we're multiplying two polynomials in a variable x. So let's say that P1, or let's say that P is A0 plus A1 x plus A2 x squared, and so on up to am x to the m. And another polynomial Q is B0 plus B1x plus B2 x squared, and so forth up to Bn x to the n. What is their product then? Let's write the product PQ as C0 plus C1 x to the 1 plus C2 x squared, and so on up to, well, it's going to be Cm plus n x to the m plus n. But what are the values of these C coefficients? This is where we encounter the operation that we often call convolution. So each coefficient of this product will be, say, C sub I, which will be the sum over, say, J and K of Aj times Bk such that J plus K equals I, right? If we want to see what the quadratic term is, what this coefficient C2 is, Well, we know that that's going to be this a naught times b2, because the term a naught times b2x squared will give us a quadratic term. But so will a1x times b1x, so we will also want to take the product of a1 and b1. And likewise, we'll wish to take the product of a2 and b0, because those are the coefficients of terms whose powers add up to 2. We just take the set of all products of coefficients whose terms add up to powers of 2, and that will give us the coefficient C2 of the product. So that is what this sum is saying. We could rewrite this sum a little more neatly. If we're summing over j, for instance, then we really only want to consider values k for which j plus k equals I. So we could multiply just by b times I minus j, and do that over all j. I won't worry about writing down limits of summation and so on. It's precisely sums of this form that are called discrete convolutions, where you're adding up all possible products, essentially, such that these indices add up to the index I. So this is an example of a discrete convolution. Convolutions also arise in the solution of differential equations, convolutions of a continuous sort, and we will especially talk about them in connection with systems and signals. So we won't dwell on them too much in the differential equations part of the course, but they'll be very fundamental when we start talking about systems. Those convolutions will be continuous time convolutions. So let's define the convolution of two functions instead of two sequences, as we've been looking at here. So given two functions of a real valued variable t, say ft and gt, their convolution is a similar kind of thing, but it's going to be an integral in this case. We'll write it f star g, so this star is our symbol for the convolution operation. And the continuous time version of that operation is much like the sum that we just saw for the case of multiplication of polynomials. We're essentially going to take the sum over all possible values of tau, of f tau times g of t minus tau. Okay. So it's just like in the example of multiplication of polynomials. We're essentially multiplying together all values of the functions f and g such that their two arguments sum to t. And that's going to give us this function of t, which we call the convolution. A little bit of terminology. When we apply this operation to two functions, we don't say that we're convoluting them, we say that we're convolving them. So the verb is to convolve. Now, the way we've written it here, it looks as though the order of f and g matters. However, by a simple change of variable, you can show that you can interchange f and g and you'll get the same result. So I won't go through the details which are given in the notes. or you may wish to do this as a simple exercise. So the convolution of f and g which is this integral f of tau times g of t minus tau d tau, is the same thing as g of tau f of t minus tau d tau, integrated from minus infinity to infinity, which we would write as g star f. So the operation of convolution is commutative. And that follows from our sort of interpretation of convolution as the operation of simply taking the products of f and g for all cases where their two arguments sum to t, and then simply summing over tau. Again, we're just taking a set of all products of values of f and g for which the two arguments sum to t. So it makes sense that it should be commutative. The order of f and g doesn't matter in that description, and indeed it doesn't matter according to the precise mathematical definition. So the operation of convolution is commutative. Now, we're interested mainly in one-sided functions. And in that case, we can write this integral a little more simply. Then f star g is going to be, by definition, the integral from minus infinity to infinity of, say, f of tau g of t minus tau d tau. Okay, but because f is going to be 0 whenever tau is negative, we can just write this as, say, the integral from 0 to infinity of f of tau g of t minus tau d tau. I'll write it as 0 minus here. But then what about g? If g is one-sided too, then g is going to be 0 whenever its argument is negative. And its argument is negative as soon as tau becomes greater than t. So in fact, we can just integrate up to t. And this is the one-sided convolution. And again, by a simple change of variable, this is the same thing as g of tau times f of t minus tau d tau, integrated from 0 to t. So this is what we'll call a one-sided convolution. And this one-sided convolution, or a convolution of two one-sided functions, is also a one-sided function. You can see that from this integral. If t is less than 0, then the integral is going to give you 0. Because you'll be integrating only over negative values of tau, so g will be 0, for instance.